好，那就这个。Can you hear me here?
Oh, no.
So, what?
Microphone.
So,
Microphone.
okay. So can you hear me?
Okay.
Yeah, okay. So, first I would like to thank Professor Chuang and Professor Chen for giving me this great opportunity to present our recent work. We are not to present our recent work to study the microstructures of complex Proboscis materials. We study this material using machine learning enabled models. So basically, we train a machine learning model such that it can evaluate the system energies, and therefore we are able to sample the microstructures of complex Proboscis materials with very fast and with good accuracy relative to density functional theory calculations. And these are two examples from our machine learning enabled molecular dynamic simulation. So this one is a MAPBI3 Proboscis, and this is a high entropy alloy material, and they are both using machine learning enabled potential energy models that I'm going to present today. So this is the outline of my talk today. So I'm going to give a very quick, brief introduction on the motivation for us to do this research. So that's basic, mostly because we are facing we have to deal with materials with very complicated, with very complex chemical compositions. And then we are going to give an introduction about the neural network potential models for domestic simulations. Then we are going to talk about the first application of this neural network models. So that's very simple MAPBI3 Proboscis materials. Then we are going to talk about our mapping of the microstructures of this formamidine, methylammonium, lead, iodine, bromine, mix, and Proboscis materials. And finally, is a conclusion for my talk. So, since this is this workshop is most of the I assume that all the attendants of this workshop are theorists. So I think I'm pretty safe to complain for all of my experimental colleagues. Well, they all outside, they don't know. So, yeah, because I think that they are very, they struggle very hard trying to publish their papers on Nature or Science. And then when they run out of their idea, the only way they can get out is to add into more and more compounds. So graphene is already, well, so now, for example, like for 2D materials, they just, they say that, oh, MOS2 is too simple. They want to put more and more stuff. So here's one crazy example, quaternary 2D material. So they basically mix the MOW, SE, and S well. They claim that by fine-tune this chemical composition, this is the range of the band gap energy they claim that they can tune. So, and also, the second one is a Proboscis material. So as we know, as you know, that Proboscis material is they have very high conversion efficiency as a solar cell application, and also there are also many other applications for Proboscis solar cell. And here is the efficiency of Proboscis solar cells going up with the year. And this paper this review paper was published in 2017, obviously. And you can see that the efficiency goes up from 14% all the way to 20 to almost 23%. And as you can see, increasing with efficiency is also the increasing chemical complexity. So you start from this very innocent MAPBI3, and then they started with the bromine, And then they start to put the formamidine, and then they start to put in the cesium. Yeah, so, but that's not the end of the story yet. Now, the structural material scientists, they found that, well, other material scientists, functional materials, and physicists, chemists, they put so many gradients into their material, and now structural material scientists, they found that, well, they can also pump a lot of elements into their materials, and they make this a high entropy alloy. And this one is a crazy example, so it's called the quaternary high entropy alloy nanoparticle. It has like a gradient, nickel, cobalt, iron, gold, copper, tin. Yeah, so, well. So you can see that. So right now we are facing this challenge that our experimental colleagues, they just have no mercy on us. And they just put more and more stuff. And then just one day just come to knock your door. Hey, Professor Bob, can you help us calculate this? We are going to submit to Nature. We believe that this paper will be wonderful. And then we are going to submit in 2 weeks.
Yeah.
Okay, so I'm going to talk about the primary subject of my talk today will be focused on complex proboscis materials. And for material scientists, they recently care very much about this process, structure, and property relationships. So I'm going to take one example for this the PSP relationship, just using this complex proboscis material. So this is I would say it's a very very detailed experiment, and apparently I feel very pity I really feel sorry for the student who performed the work. Well, so they basically have this many compositions for FAMA here, and iodine and bromide concentration. They made this many FAMA PBIB hard solar cell samples, and they take the SEM pictures. So this is the surface topology, and here they actually map the performance, conversion efficiency, the open circuit voltage, the short circuit current density, and the filling factor. Yeah, are the function of all these compositions. And they basically correspond to, so for example, for this efficiency and JSC, VOC, they correspond to process because that's the composition and property, JSC, VOC. And for this, from visualization and also from SEM feature, we got an idea about we have an idea about the process, composition, as well, and structure. However, the information in the structure, we only have SEM features, and this from director visualization, and we have very limited information here. And we have no microstructure details. We have no idea about lattice distortion induced, because we know FA and MA and the bromine and iodine, they have different ionic size. And we have no idea if there's any like phase segregation, domain boundary, whatever. And we also have, and therefore that means that we cannot really construct this property, the process structure property correlations. And therefore, for the poor students or poor postdoc, he can only rely on trial and error. Now we want to see if computer simulation can help. But speaking of computer simulation, for this chemically complex material, one of the biggest challenges is because there exist many possible permutations. Like this, you've got like a 50-50 composition, but you have many possible permutations. And this is just a binary, and we are talking about FAMA IPR. So there are actually 4 components. So for first principle calculations, of course it is very accurate and has very high transferability. But however, the price to pay is that you can only work on small system, and the calculation speed is slow. So for example, like this work was done by Professor Grezzo's group and his simulation colleague. They try to estimate the mixing energy, mixing free energy of this Fa, CCN, and iodine. And you see, so this is the CCN concentration. And for each CCN concentration, because you must consider this permutation factor. So for each concentration, they can only take 10 possible permutation and take the lowest one as the delta E inputs. So this sometimes is not so you see, because for this material you can have many possible permutation ways, and you only 10 sounds like 2 little. But however, that's the best that they can do because of the limitation of first principle calculation. And the other possibility is to use classical MD simulation. So of course you can see that classical MD can deal with a very large system like this, and it's very fast. I know that for some of the computers, like the DE shell computer at home, if you spend 1 month, you can compute the MD for like 1 millisecond. Yeah. But however, the problem is accuracy. Well, especially for a complex system like the Proboscis. So now we are facing the problem for most of the current atomistic simulation tools, as you can see from here. So for first principle calculations, we have good accuracy, but however, we are limited by the system size and available time scales. And for classical MD, well, I would say system size is not a big issue, and the simulation time is also not a big issue. But however, the accuracy is questionable. So here we want to see if we can harness if we can leverage machine learning enabled models so that we can have both accuracy and we can also have a decent system size and also faster computational speed. So here is a very simple example of a neural network. So it's basically can be decomposed into three layers: the input layer, the hidden layer, and the output layer. So the input layers is basically different input vector. So it goes through this hidden layer. So the neuron here, the value is basically the input times a weighting matrix here, the weighting parameter here, takes summation, and then goes through bias and goes through an activation function. And if you repeat this for the first layer, then you got all the numbers of the first layer, then the outputs go to the once again to the weighted summation, and it goes through the bias, and once again activation function, and repeat this all the way to the output layer. So this looks like a very complicated, but I have a very simple way to illustrate how the neural network actually looks like. And unfortunately, I have to speak in Mandarin right now because I'm not good for this kind of stuff. Okay. Imagine. So this is a very simple example. The input layer consists of a vector of the year you were born, the date you were born, the time you were born, and the location you were born. And the first neuron is astrology stuff. I'm sorry for this non-Chinese speakers. I don't know if you can look at this. So here's the 太阳星座 第一个 neuron. And the second neuron is a 月亮星座. And you got the rest neuron at the 上升星座水星 and the 金星. Mercury, Venus. And then, if you're going all the way through all this hidden layer, you got output. Yeah. You got a creepy appearance, you got an abnormal inside, and your love luck is like, well, this is how, I think it's a very simple way to illustrate what does the neural network actually mean. Okay, so now I'm going to talk about I'm going to talk about how we can describe system energy of material of an atomistic system using neural network. So we use the energy partitioning scheme proposed by Bader and Nat'l. And the advantage of this scheme is that it can be extended to systems of arbitrary atoms. So we start from Cartesian coordinate of the system. So you got a Cartesian coordinate of all the system, and then we convert them into the feature vector of each atom. So this basically is correlated with the chemical environment of a given atom. Then for this feature vector G, it goes as an input, it goes through an atomic neural network. So this is the reason why it can be extended to system of arbitrary size, because each atom is evaluated. The force and energy of each atom is evaluated in their individual atomic neural network. And then finally, we decompose the whole system energy into this E1, E2, and E3, all the way to En, and the summation. And you got the total system energy as a summation of this. And this is how atomic neural network looks like. So we started from this G feature vector and then going through all this hidden layer and then output the atomic energy. And the derivative of this is atomic force. And the training procedure is that we need to first prepare a training set comprising of a number of images of system with atomic coordinates labeled by energy. This energy can be either from EFT or from lottery. Well, you just need to have labels for structure and the resultant either energy or, yeah. And then you generate an initial gas and the initial gas of atomic neural network, and then you get an initial set of predicted energy and force. Then you compare with the labeled the correct answer, computes the loss function, and then you use an optimizer to update the weighting matrix, the weighting parameters connecting all the neurons, and doing this again and again until the loss converge. And here, because I have limited the length for this slide, so I only put using energy as the target. But actually, we can also include atomic force into this loss function. And this is how the atomic neural network looks like. So this is the input feature vector, and this is one example for copper in CZDSE material. And the red means the positive number, blue means the negative weighting number, and the thickness of the line corresponds to the absolute value of each weighting parameter. And for materials of CZTSE, you need to prepare 4 different atomic neural networks for each element. Okay, now let's move to the MAPBI3 Proboscis material. So we start to generate the training set using the trigonal Proboscis crystal, and we generate training sets by running vast molecular dynamics simulations at 300K, And in order to increase in order to sample as much possible feature vectors space as possible, so we also applied hydrostatic strain ranging from -5% to +5%, and we use both energy and the force training. So we basically here we tested 3 different training settings as shown here. So this shows the architecture of the neural network and potential energy models. So here for lead and iodine materials atoms, we all have 3 hidden layers, and it has 10 neurons, 5 neurons, and 5 neurons for each hidden layer. And for carbon, nitrogen, and hydrogen atoms, for the first setting, for the setting 1, it also has 3 hidden layers and 5 neurons for each hidden layer. But for the rest 2, we only have 2 hidden layers and 5 neurons in each hidden layer. And for the setting 3, in addition to just using energy as a training target, we also incorporated force, atomic force, as a training target. And here's the training results. So the training results is that, so as you can see for the training set, for training setting 1, you can see that, so the vertical, so the horizontal axis is the energies from VASP, and the vertical axis is the energy predicted from the neural network models. You can find that they basically lie on this diagonal line with a very small error. So this is much smaller than the thermal energy at 300K. And for setting 2, once again, it's also in very good agreement with that from VASP. And for the setting 3, because we also include, for the setting 3, just looking at the energy, also in good agreement. And if we look at the force, once again, even for atomic force, so this is a force from VASP, and the force predicted from a neural network model, also in very good agreement. And because our training sets were generated using tetrahedral Proboscis, and then we also compute the potential energy curves of both cubic and also rhombic MNPPI3 using this neural network potential models. And here's the results. So this is a different lattice parameter size, and you can find that this is from VASP, and for 3 different models, they almost overlap with those energies from VASP. So this is for cubic Proboscis, and this is for also rhombic. Once again, the agreement is very good. And we also carry out additional validations because we happen to run into a very picky referee. So yeah, so validation is that we run 2,000 steps of ab initio MD of cubic Proboscis, and the training set was, I need to stress out once again, the training set was generated using the tetrahedral Proboscis. And this is structures from, so this is red line. Well, it's hard to see the red line, the black line is from VASP, and the red line is from neural network potential model. You can find they almost coincide with each other. So this is for setting 1, and for setting 2, once again, they also overlap with each other very good. And the third one, there's still very good agreement. But if we look at the force, you can find that for the setting 3, which we also put force explicitly as a training target, you can compare the difference in the accuracy in predicting the force. This one, still very good, had a very good correspondence between VASP and the neural network model. But however, for this 2, training without atomic force, you can see some scattering here. Well, And we also compute the direction parity. So this is the angle difference between vascular force and the force predicted from neural network model. You can find that 91% of the force predicted is within the 20-degree difference comparing with VAS. So even the force direction is very good. So we know that the neural network potential model can basically reproduce the force and the energy from VAS. But what about the benchmark? I mean the speed, computational speed. So what we did is that we implement the neural network potential models into LENS, molecular dynamics simulation package. And we just introduced a new concept here. And this work was done by my postdoc, Nat'l, and also another postdoc, Nat'l. And here is the benchmark. So this one is the number of atoms. We start from 100 all the way to 0.1 billion atoms. Yeah. And this is the time required for each step. And these are from VAS using CPU and also from GPU, 1 GPU, 4 GPU. And this purple line is from CPU, and just use 16 cores. And you can compare for a system of 2,500, almost 2,600 atoms, using neural network potential model, it's only like slightly longer than 0.1 second. And this is only on 16 cores. And for VAS, it takes like, well, 3 hours. Yeah, more than 3 hours. Yeah. So this shows that by using neural network models, using neural network energy models allows us to give us the possibility to sample the configurational or permutation space for complex materials in an exhaustive manner. Okay. So now so now we are going to play with some really complex system. So this is FA, MA, PV, IVR mixed diamond Proboscis, as I said before. So in this system, there are 1, 2, 3, 4, 5. Yeah, 5 different elements, and actually there are I think there are 6 elements. So yeah. So this is how methylaminium molecule cation looks like, and this is for mammalian cation looks like, and this is the crystal structure. And the training set is that we start from MA, FA, I, and BR with a variety of concentration, and then we also take different permutation for here. Oh, I got 40 minutes, but now it's only 30. I think I got. Okay, so. Okay, so this is the training results. So this is from VAS, and this is from neural networks. So they are in very good agreement for both energy and force. The next thing is that we want to perform Monte Carlo sampling for this FAMAPDIBR system. So we start from initial structure, then we do random FA and MA swapping or bromine and iodine swapping, and then we randomly locate the cations, then do minimization, update the structure, record the energy. So we sample this many different concentration of methylammonium and the bromine. So we actually performed the 81 concentration. So I need to update this number. And for the whole system, there are like 1,700 atoms. And for each concentration, we performed 10,000 Monte Carlo steps. Namely, we sampled 10,000 different possible permutations. And this is a histogram of all the 10,000 structures we have. And if we we isolate the structure with the lowest energy, shown here, and you cannot really see many things here. But before this, we need to first do some small validation. So this is the band gap we compute from TFT. But I have to stress out that because there are 17 country atoms in our system, so we only take gamma points and we just take a single point. There's no relaxation. We just directly use the structure, the lowest energy structure from new network potential calculations, and just do gamma points. And of course, you can see underestimate here. But you see the trend is fine. And I guess this 2 points, there must be something wrong with the experiment. Okay, so now we can compute the mixing energy. So this is the mixing energy. So this is the map of the mixing energies. You can find that in the concentration A, what you would expect is that the energy landscape looks like this, and you would anticipate that in this region you have a solid solution with a concentration C, with the bromine concentration Ca. However, in the region B, you would anticipate that phase segregation might happen, which looks like this. So the energy landscape in B looks like this, and the system can actually drop to a lower energy state by segregating into this phase and this phase. So you would anticipate that here the system might comprise of 2 different phases. So we also want to sample the short range order. So we use this short range order parameter. So it's basically here we have a nominal concentration of B, and here is the actual AB bonding probability from our simulations. So we know that if this guy is bigger than 0, that means that AB pairs, atomic pairs, they tend to segregate. And then we basically take 3 different categories: low energy, mid energy, and high energy regime, and to sample this short range order parameter. Oh, I'm sorry. So here we only show the lowest energy, the short range order of the lowest energy structures. So here you can see that for MA and FA pairs, we got phase segregation here. We got segregation of MA and FA pairs and bromine and iodine pairs here. Okay, so the next thing is the atomic strength, the map of the atomic strength. So here you can see that for when energy drops, the atomic strength also drops. So these are for all the different elements. So no matter the concentration, when the system energy drops, the atomic strength also drops. And this is the map of all the atomic shear strength. So this is the average, and this is the bromine, iodine, lead, methyl aluminum, and the bromine. And then finally, we have done this many methods, and this one is from experiments. And we want to see if we can concentrate everything. We want to plot everything into one single Pearson correlation matrix, so that we can review the process structure and the property relationships. So this is the process, and this one is for structure property, and this one is for property. So we started from structure correlations. So we can find that with a high mixing energy, we got the preferential MAI bonding, segregation between MA and FA, and the bromine and iodine, and also increase the strength. And then we can also find a strong lattice distortion with also coming with all this phase segregation and preferential bonding. And about this process and the structure, we can find that bromine concentration has strong correlations with mixing energies. And we can also find that bromine concentration is strongly correlated to the segregation of Ma and Fa, and bromine and I, and also strength. So we know that bromine concentration is very important. And finally, let's look at the property and structures. So we know that the mixing energy is negatively correlated to conversion efficiency and short circuit current density. We also notice that once again the conversion efficiency, short circuit currents are inversely correlated with phase segregation. And finally, we notice, so we can reach the conclusion that when you have lattice distortion, when the lattice distortion drops, we have to look at here. So when we have a strong lattice distortion, this leads to high mixing energy, and this is going to trigger phase segregation. So it's going to segregate into phases with not so distorted. As a result, you have a domain boundary, and this is basically create a lot of defect. So this is not good for carrier transport, and therefore leading to the decrease in the efficiency. So this is the summary for my talk. So we start from DFT. So the accuracy is good, but the size and time is not good. And for classical MD simulations, we got the size, but we sacrifice the accuracy. And we think that the machine learning enabled models, we still sacrifice the accuracy, but not as much as classical MD. And we also get, however, we get a huge gain in terms of system size. Finally, I would like to thank the funding from Seneca and MOS, and also thanks my group member here. So finally, thank you very much for your attention.
Thank you. Now, any comments and questions?
Hello. Thank you very much, Professor Chun-Wei, for the talk. I have some questions regarding the methods, because I'm fairly new to learning neural networks. So one of my questions is that how are you able to define, identify the important hyperparameters in this neural networks? And second is, how were you able to initialize the weights? Did you randomize it, or did you base it on specific studies? And the last one is, did you use any special packages for generating your neural networks, or did you create your own neural networks? That's it for me. Thank you.
Okay, so very good question. So for the first question, the hyperparameter. So for the hyperparameters, we basically use first we start from trial and error, and so that takes a lot of time. But recently my students start to transfer to write another optimizer to wrap. Just use hyperparameter as another parameter to optimize. But yeah, I know this sounds fun. And your second question is
regarding the weights. How are you?
The weight. Okay. So the weight we basically start from random. We start from random because this is not a very complex neural network, as you can see. We only have like 3 layers or maybe 5 layers. So that's not a very complex. And about the third, the training part, we use the AMP package. But because AMP package was written in Python, and when you actually perform MD simulation, it was like super duper slow. like I didn't show the benchmark for the Python part, so I decided to rewrote that in C++ and just throw that in ULANS. And the speed got drastically increased. And now we also have our own training code, and it's still under testing. Yeah, thank you.
Any other questions or comments?
Teacher, I have a big question about the prediction, the phase segregation. I don't know. I don't understand how you predict predict whether the phase segregation will happen or not, based on what factors. And finally, the most important, what's the composition of the phase segregation? How you predict this information?
Okay, so that's a very good question. So I think I didn't have. Okay, so I need to go back here. There we go. So from here, you see, I need to roll all the way here. Okay. So if you look at the concentration here, so its energy looks the energy landscape looks like this. So you start from here. So but note that when you so this one it certainly has a higher energy, right?
Yeah.
So it want to go elsewhere, but it cannot just go this place, because if they go this place, then the concentration is not right. So if they want to keep the concentration, because you see the mass is conserved, so it has to stay here. So the only way it can reduce the energy while keeps the concentration the same is to drop here and form two phases. And if you do the linear form two phases here and here, if you combine, so the concentration of bromine is here and so you basically can do the linear interpolation and make the system free energy drop to here by segregating to this phase and this phase.
But it is binary system. For binary system, it's very easy. But for high entropy system, there are almost five.
Yeah, this is just schematic.
Oh, just schematic.
Yeah, I know everybody starts from binary, and it's easier to plot the binary. But in this system, you see the reason why I plot this two different arrows, because I don't know where it goes.
Oh.
Because here for this system, we are no longer talking about common tangent line. We need to find a common tangent plane.
Okay. Thank you.
Okay, thank you, Professor Paul, for the nice talk.